This is Algebra 2 with Trig, working on Unit 2A review. This first question, we're trying to determine if this is a polynomial, and looking at its format, I notice that the x's all have positive exponents, and it's okay to have a square root on a number because that's a real value. So we're going to rewrite in standard form. F of x, you need to write it with the largest exponent first. So x to the fourth, so the 8 goes with it and the negative goes with the 8. So it's negative 8x to the fourth, then a positive 2x cubed, and a positive 5x squared. There is no just x term. So when you're writing it in standard form, you do not need to put down 0 x's. This was a polynomial. It's a degree of 4, but more importantly than the degree of 4, we like to talk about it is an even degree. If you want to also state that it is 4, that's fine, but in a lot of other spots we like to talk about if it's even or odd degree, because that makes the equation act differently. The type of equation that it is a quartic. Because it's 4th degree, it's kind of like a quadratic, falls underneath the term quartic. The leading coefficient, we see that it's negative 8. More importantly than the negative 8 part is that it is negative. If you want to state that it's a negative 8 specifically, that's fine, but the negative is what we're looking for. That is what affects how it acts on a graph. Here, when we look at this polynomial, we see that it has a negative as an exponent. That's actually going to put the x into the denominator. As the negative exponent puts it into the denominator. That limits what x can be. So that does not make it a polynomial. It's still a 5th degree, but it's not a 5th degree polynomial. Still has a leading coefficient, but it's not a polynomial. Synthetic. When we use synthetic, the first thing we want to notice is x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, x to the 0 power. Every term is represented. So 7, negative 3, 1, 5, negative 9. We put our organizer around it with x equals. We need to know what x equals. In the future, that's going to be a big deal. So x equals 2. We're going to drop down our 7 and multiply. Add these two together and multiply. Add these two together and multiply. Add these two together and multiply. And add these two together. So f of 2 should equal 93. I've already worked through this one, but we can see what x equals. X equals negative 2, so we place negative 2 on this side. Rewriting it in standard form puts the largest exponent first. Notice that there are no x cubes. So in this situation, when we're looking for coefficients, it's very important to identify that it's a 0 as a coefficient and 0 for a coefficient of the squares. It has 7x and a positive 1. So when I write down my coefficients for my synthetic substitution, you would want to use a negative 1. You must put in zeros. Otherwise, you're working with not enough terms to represent that this is a quartic. Drop down your number and multiply. Negative 2 times negative 1 is 2. Add them together. Times negative 2. Add them together. times negative 2 times negative 2 and add them together. So f of negative 2 is negative 29. Coming on over here to our graph, we notice that this is in factored form. It shows our factors. So we're looking to see where this equation hits the x-axis. Where is this equation equal to 0? This will become 0 when any of these three factors is 0 itself. So when x is 0, or x minus 2 is 0, or x plus 3 is 0. Now I did write it twice because the x plus 3 is in parentheses. That's reminding me that this is a double 0. So I plot my point at 0, at 2, and at negative 3. Now what does a double 0 do? It tells you that it bounces at that particular location. It goes all the way through the 0 because it's called a single or a linear 0. And then it goes all the way through at 2 because it's a single or a linear 0. We know it goes positive up to the right because the leading coefficient is positive. And we know since the degree is even, there would be 1, 2, 3, 4 because it's there twice. 1, 2, 3, 4. That's here twice. It's an even degree. So we know that this side is going to also go up. Then we can bounce it and flow through the rest. The end behavior, as x approaches negative infinity, the function approaches positive infinity. As x approaches positive infinity, the function also approaches positive infinity. Here we have one factor, two factors, three factors. None of them are doubles, so this is considered an odd degree. The leading coefficient is negative 2. The main thing we're interested in is knowing that it's negative. Since we're working with x plus 4, we know that x is going to be negative 4. That makes it a 0. X minus 2 gives me a 2 as a 0. And x plus 1 gives me a negative 1. Because this is a leading coefficient that's negative, it's going to fall to the right. Because it's odd, it's going to be going in the opposite direction. Notice that even when in the same direction, odd will always go in opposite directions. The rest of it is just going to flow right through. We're not worried about just how high and low we go. Just curve down below the x-axis, curve up above the x-axis, come through. As x approaches the left, you can see that g of x is going up. And as x moves to the right, you can see that g of x is going down. Here we have x plus 1 squared, so that makes it a double 0. We could rewrite that if we like. X plus 1, x plus 1, and then x plus 3. So we know that there's a double 0 at negative 1. We have a 0 at positive 3. We know it's going to bounce at that location. We know the degree is odd because it's a 3. There's 3 different terms. The distinct number of zeros, the actual spots where the graph is going to touch the x-axis, is 2. And the turning points, let's see what happens. That's always going to be n minus 1, the degree minus 1. Since the degree is 3 minus 1, we're expecting there to be 2 turning points. Because this was a negative leading coefficient, we know it's going to fall. Because it's odd, we know it's going to increase in the opposite direction. And from there, it is... Oh, we do have a double zero. I almost said that wrong. I may have. We have a double zero. I was thinking it was going to flow through, but it can't flow through and go up. But we have that double zero. I'd written it twice. Here we're going to factor completely. We're looking for two numbers that multiply to be 63 and add to be 16, or negative 16. That's going to be negative, I was going to go with negative 13 and 3, but 13 and 3 is only 39. So 7 and 9. They're both going to be negative because they multiply to be 63. Negative times a negative is a positive. And when they add those two numbers together, it's a negative 16. So when you factor, you don't solve. When you factor, you just find the factors. You break it down into the parentheses. Now this is a little bit different. We're not working with just 6. We're working with the 2 and the 6. This one we are working with the 1 and the 63. We just called it 63. But if it has a leading coefficient other than 1, we have to incorporate that. So we're looking for two numbers that multiply to be negative 12 and add to be 1. That's going to be negative 3 and 4. So to do this, we could use a guess and check format, or we could use factor by grouping. So I'm going to use factor by grouping. We'll call this 2x squared minus 3x plus 4x minus 6. Notice that my first term gets written down first. My x has to be broken down into the numbers that we determined was good to make negative 12 and good to make 1. They add to become 1x. So that's why we're going to use those numbers in place of the 1x. And then write my 6 down here at the edge. Now here's the grouping part. We're going to group up our first two terms and factor out what we can. That's a GCF. That means we're going to leave a 2x and a minus 3 inside. I can bring down my sign, factor out what I can. I see they're both even numbers, so I can factor out a 2. That leaves me with 2x minus 3. Notice inside my parentheses is exactly the same. So that's going to leave me with x plus 2 and 2x minus 3. I should be able to multiply those back together. 2x squared, negative 3 and a positive 4 gives me 1 and negative 6. This one is the difference of 2 squares. So that means, can we take the square root of 9x squared? Well, yes we can. Can we take the square root of 25? Yes we can. Is the middle term minus? The middle term has to be minus. If that's your pattern, if we can do that, if this is a perfect square and that's a perfect square, we have a shortcut to factoring this. It's just 3x minus 5 and 3x plus 5. Together they would multiply together to make 9x squared. A positive 15 and a negative 15 make 0 in the middle, and then negative 25 at the end. We're going to create a polynomial with a degree of 3, 2 distinct zeros, and a negative leading coefficient. So if it helps you to make a little sketch, you want 2 distinct zeros. So I got 2 distinct zeros. It's got to be a degree of 3, which means it's got to go in opposite directions, but the leading coefficient's going to make it come downwards. So they got to go in opposite directions. It's going to have to bounce somewhere. So I'm going to make it bounce over here. So f of x with a leading coefficient that's negative is going to have an x plus a number, whatever this might be, squared, times x minus something that moves us over here on the right-hand side. There's an infinite number of answers you could use here. I don't expect yours is exactly like mine. You could have made it bounce over here on this side. It would not bounce in both spots because then it would bounce up. Here we're going to create a polynomial function with the same end behavior as a quadratic. That means it's got to be going up and it's got to be going up just like a quadratic would. It's going to have a positive leading coefficient, but it's going to have 4 x-intercepts. So it would come down and go through and come down and go through. So to make it a different function, we're going to have x plus a number out here and x plus a smaller number, and x minus moves it to the right, and x minus is also to the right. Any values inside there you want to use, it's got to be a positive leading coefficient, so I'm just going to call it positive 1. Create a polynomial where these are your intercepts. We have 0, 0, we have 9, 0, and we have negative 7, 0. It's got to have the same end behavior as x squared. So that means they both have to be going up. Now this only has 3 zeros. If we just floated through here, we couldn't, it would fall to the right. So it's got to bounce at one of these spots. You can bounce anywhere you want it to bounce. So I'm going to bounce it here. Makes a W. So we'll just make up what this equation looks like. K of x, we'll call it a new name. It's got to be over here, which would be x plus some number. Oh, it's got to be exactly, if it's going to go through negative 7, it's got to be exactly x plus 7. And if it's going to go out here at 9, it's got to be exactly x minus 9. Now, how do we get this value here? To make it go through 0, 0, I need x minus 0. It would be better just to call it x. And in my situation, I squared it. I bounced it at that spot. That gives me 1, 2 factors, 3, 4. That makes it an even degree, which goes up just like x squared. Describe the end behavior. Well, here we have a leading coefficient that is positive. We have a degree that is negative. I'm sorry, that is odd. There is no negative degree, not for our polynomials. So this is odd. So what that's going to look like we know for sure that it is a degree is odd, so they're going in opposite directions. It's going to be going up and it's going to be going down. If the leading coefficient is positive, we know it's increasing to the right. If the degree is odd, it goes in the opposite direction. So as x approaches negative infinity, I know my f of x is going to be dropping. As x approaches positive infinity, I know my function is increasing. I don't really know what's happening in the middle, but be something close to that. It probably doesn't even go through and touch the x-axis twice. It's missing a lot of terms. But the end behaviors guarantee to be this. Here, my leading coefficient is negative. So because the leading coefficient is negative, as x approaches positive infinity, I know my function is going to be dropping because of the negative leading coefficient. And because the degree is even, I know that it's also going to be dropping when we go to the left. Here we can use our graphing calculator. It wasn't in the graphing calculator section, but we definitely can. This is a graphing calculator question. The data in the table below give the average speed of the Trident motor yacht for several different engine speeds. So if the RPM increases, this is what we get. So we're going to go to Stat, which is right here. That gives us a screen that looks like this. We go to Edit, so we can put in our information. And it looks like we have information in here already. Now, what's going to be good to do, and I say this to the class a lot, second plus 712, and it clears everything out. So when you go back over to Stat and Edit, you don't have any information in it. There's multiple ways to clear it out. That just helps be sure that there's no other errors that are going to occur. So our x values are 9, 11, 13, 15, 17, 19, 21.5, 6.43, 7.61, 8.82, 9.86, 10.88, 12.36, and 15.24. Notice that the number of x terms and the number of y terms has to be exactly the same. You'll get an error. We want to take this data, which are just points plotted on a graph. You want to think about what that might look like. When we're out here at 9, we're up at 6. Out at 11, we're up at 7. Out at 13, we're up at 8. Out at 15, we're up at 9, almost 10. 17, we're up at 10.8. 19, and 21. So we have this curve that's coming through. Looks a little linear to me the way I've made my plots in here, or it could look a little quadratic, but you might even say that it looks a little cubic. Okay, they're asking for us to find a cubic model. So we're going to take this data and go to Stat, over to Calc, and down to Cubic, which is number 6. Enter. Now your screen might be different here. It might show different lines with other information like L1 and L2, and then it says Calculate near the bottom. Just arrow down or hit Enter till you get down to Calculate and hit Enter. And this is what we should all have. You have your A term, your B term, your C term, and your D term. Here they're telling you exactly what that A, B, C, and D equals, or stands for. We have 4/7 or 4/8. Looking here, we would actually round that tenths, hundredths, thousandths. So since that's a 7, we'd call that a 0.005. This is a cubic equation. Minus 0.194x squared plus 3.13x minus 9.53. 0.005, negative 0.194, 3.13, and negative 9.53. So, if we have the RPMs, okay, here we're looking for our RPMs to be 2,400. So that is going to be our X, our speed, which is X, which is in RPMs. So what's going to be best here, we're not looking for a Y value, we're looking for an X value. We can't go to table yet because we have no values in our table. We need to go to Y equals and type this in. 0.005 x cubed minus 0.194 x squared plus 3.13 x minus 9.53. Now when I go to table, now I actually get my values. And they should be somewhere close to what's in your table. At 9, we're at 6 something. At 11, we're at 8 something. Well, that's a little high in the graph than it is on the table, but we're taking averages all the way through to try to be the best we can to go between each one of those. Well, we need to be way up high, and this is going to take us forever to get up to 2,400. Okay? I don't want to sit here that whole time to do that. So there's fun ways around this. You can do second window, which is table set. And you can start your table at 2,400. Then go to table, and there you are at 2,400. We are a really big number. Put your cursor right on it, and it'll show you the difference between these different values. They look all the same just because they're rounded, but they're all a little bit different. So, that looks like 68 million. 10,000, 62.47. Seems a little unrealistic, but in terms of our data, in terms of our model, at this many RPMs, which is a little crazy compared to what we had down here, that's what we got. Oh, wait, hold on, hold the phone. I just messed this up. This says in hundreds of RPMs. So we want the number 24. We want the number 24 because that's 2,400. That makes so much more sense. Yikes. That was a little crazy. Just had to think if my data made sense. All right, so we don't want 2,400. We want 24. That's going to be 22.96. That's so much better. 22.96 knots. Glad we figured it out. Here we have the rest of our calculator section. We're taking our cardboard. I've done this with the class before. We're going to take a sticky note. I'm going to cut off the sticky part, and that's going to represent a cardboard piece for us. And on this cardboard piece, we're going to have 16 inches going one way and 20 inches going the other way. So it's a big cardboard piece. So we're going to make a box, and it's going to be formed by cutting length X in the picture. We're going to cut these squares out. So we come over here and I cut a square off from this side, and I'm going to try to cut the same size square off of all four corners. Something like that. So remember, if it was 16 all the way across, this portion is no longer 16. This is 16 minus this amount, which is X, and this amount, which is X. So it's 16 minus 2X. And this portion, going right to left, the whole distance was 20, but if this is X, X by X, and this is X by X, this is 20 minus 2X. So this dimension in here. So we can then fold up the sides of our box, and you see that it is not the original width of the cardboard. It's no longer 20. It's smaller than the cardboard was originally. So we have our volume to be 16 minus 2x and 18 minus 2x. Now we also have a height going on in here. Length times width times height, that's volume. So our height, if we cut the x out, the height of the box is also x. So to determine what dimensions we should use, second plus 712, so all my values are back to normal. I'm going to go to my y equals x, 16 minus 2x, 18 minus 2x, and I can go to table and we can see what falls through here. Alright, we see a little bit coming through here. If I go to my table, second graph is my table, I can see that by the time I get to 3, I have my highest value, 360. So I need my window to have a y value that's bigger than 360. There it is. I want to know what this value is up here. So second trace, we're going to do our maximum. We do right bound, enter. Oh, that's left bound. This is right bound, enter. And then I can put my cursor right back on top where I think the answer is if I wish, and I can get my two values. This is telling me how long should each cut be. The x value is 2.82. These are inches. Rounded to the nearest tenth, that would be 2.8. What is the maximum volume? The volume is 361.09, which you round up one number, which rounds up the next number, which gives us a 1 there. These are inches cubed. And the dimensions, x is going to be 2.82. 16 minus 2 times that amount. (16 minus 2 times 2.82) is going to be 10.36, and 20 minus 2 times 2.82 gives me 14.36. So my 14.36 times my 10.36 times my 2.82 should give me an answer that is very close, maybe not exactly, but very close to my volume. I don't see it. 1 second. All right, let's take a look back. I went through my calculations. They're all making sense. If you look back at my equation I typed in, you might remember I typed in 18 minus 2x. This should have been 20 minus 2x. Makes my graph go up a little bit higher. How much higher? It goes up to 420, so I need to pick a window bigger than 420. So now when I do my second trace, I do my maximum, which is my left bound and my right bound. I'm going to get a 2.9, my bad, 2.94. And I have a maximum volume of 420. Good thing I checked my work. So I have my dimension of 2.94, 16 minus 2 times 94, 20 minus 2 times 94. So 16 minus 2 times 2.94 is 10.12, and 20 minus 2 times gives me 1412. Very similar type numbers. So I have my 1412 times my 1012 times my 294, and shabam, I got the exact same value. Love it when a plan comes together. Alright, we're going to come down here to this equation. We're going to go a second plus 712, so nothing's crazy. All my settings are as yours should be. X to the 5th plus 2x squared minus 17x minus 4. When I graph this, graph goes way up, way down. Let's take a look at our table to see just how far it's going up. Looks like it's going up to 14, so I need a number bigger than 14. Looks like it goes down to negative 18. So I need to go up to something bigger than 14 and down past something smaller than 18. And there they are. Now it's a little bit easier to see. So here are my x-intercepts. So second trace, go to 0. I need to be left of my answer. That would be left of my answer. And right of my answer. Hit enter. So I have an x-intercept at negative 2.1 because we would round. Now this is funny. This is negative 1 e to the negative 12. This is essentially 0. It means exactly 0. It's just the way the calculator figures it out. And then we do second calc 0. Now we need to be to the left, because it says left bound, left of the answer we're looking for, to the right of the answer we're looking for, and hit enter. That's going to be negative 0.23. This one gives us exactly 0. That was handy. And then we have another 0. We are to the left of it, enter. We're to the right of it, enter. And I get 1.97 comma 0. This is essentially 0. This is 11 decimal spots to the left of the 2. You're going to move 12 of them, but the decimal spot is after the 2. So 12 of them. 0.00000000000 negative 2. Okay, local maximum. Local maximum, we go down here to maximum. We have to get to the left bound of it, so we get to the left of this highest point, enter. Get to the right of the highest point, enter. Just hit enter again, and that gives us a negative 1.46 and 18.45. Then we have a local min. So second calc, go to min, get to the left of it, enter. Get to the right of it, enter, enter again, and that gives us 1.25, negative 19.07. And our y-intercept, well, our y-intercept, we don't have an operation in our calculator to find that, but it is right here. Good luck, everybody.